So welcome everyone to the discussion session of the summer school, CPBS summer school. And then today we're going to talk about statistical mechanics approach to biological physics. The three of us are going to go through those two papers you read with you and answer your question. So first, let us introduce ourselves. So my name is Xiaowen, and I'm a graduate student in physics.
I'm Caroline. I'm also a graduate student in the physics department here.
Hi, I'm Kamesh. I'm one of the center fellows, and I work on problems at the interface of machine learning, biophysics, and neuroscience.
Okay. So Kamesh, yes, thank you. So today we'll go through three parts. So Kamesh will first give us a primer on the probability theory, and then Caroline will explain in detail how maximum entropy models work, and then I'll finally address basically detailed questions of the two papers connecting physics and biology. So at the end of each session, we're going to have a Q&A break, so we will answer the questions you have. So as we're talking, you can just leave your question in the Q&A session. So either it will be answered by one of us through chat, or we'll answer it in the Q&A session. Okay, so Kamesh.
Perfect, thanks, Xiaowen. So I'm going to give you a brief primer on some topics in probability theory which are relevant to the talk this afternoon. And the place I'd like to begin with is, let's talk about, start with what's a random variable. And random variables are used to model unpredictable phenomena. And so when a phenomena can take a certain set of outcomes, which formally belong to a sample space omega, what a random variable does is it maps each outcome of the process you're modeling onto a real number. And associated with each outcome is some probability of occurrence. And the probability over all the outcomes should sum to 1. That's sort of the formal setup. And depending on the phenomena you're modeling, the outcomes can either be discrete values. So for instance, if you're thinking about flipping a coin or throwing a die, you'll have a discrete set of outcomes, or it can be a continuous set of outcomes. For instance, what's the temperature at a place on a certain day of the year? And so with that setup, just to give you an example, if I'm thinking about a fair coin, then the two outcomes which I can expect are heads and tails. So the sample space omega will be heads and tails. And the random variable, which maps from the sample space to some real number, so let's say 0, 1, but it's not important what they are, will just be a function mapping heads or tails to those two numbers. And for a fair coin, the probabilities associated with the outcomes will be half, 1/2 in each case. Now, let's take a closer look at how the probabilities with respect to outcomes are represented. And for discrete random variables, which take on a discrete set of values, the probabilities are specified by something called the probability mass function, or the PMF. And so for instance, if you have a 6-sided die, which can take on 6 possible outcomes, the probability of each of those outcomes is 1/6. And so the PMF will be given by this function over here, which is 1/6 when you have one of those outcomes and a 0 otherwise. For continuous random variables, the probabilities are specified by something called the probability density function. And strictly speaking, the probability that a continuous random variable takes on any specific value is 0 in general. But one can talk about what is the probability that the random variable lies in a set, say an interval, which is bounded by A and B. And that probability will be the area under the PDF in that interval. And the PDF or the probability density functions, a few facts about them: they have to be non-negative, and they have to integrate to 1. And to give you a little more feel for properties of these, let's look at 2 commonly encountered PDFs, and this will be somewhat relevant to the papers and also the talk later in the afternoon. So the first PDF we're going to look at is that of an exponentially distributed random variable. And the PDF is given by the following formula. So it's 0 for all negative values of the random variable. And for positive values, it's given by this exponential form. And the place where this PDF often comes, the exponential PDF often comes up, is to model the time between events in a process where the events are occurring continuously and independently. And it'll turn out in statistical mechanics, where the Boltzmann distribution is one of the central objects, the Boltzmann distribution also follows a similar form. And there's one parameter in this exponential PDF, lambda, and you can see some examples of how the PDF looks for a few values of lambda. And as lambda becomes higher, you get these steeper decays to 0. And what that means is, as lambda increases, it's much more likely that the random variable is going to take smaller values. And the second PDF which I want to talk about, which many of you might have encountered before, is the Gaussian PDF. And this is ubiquitous in many branches of science. And part of the reason for that ubiquity has to do with something called the central limit theorem, which says when you sample a random process many times, the average of all those samples under broad conditions will be distributed according to the Gaussian PDF. And you've got 2 parameters specifying the Gaussian PDF, mu and sigma. And just very briefly, what these 2 do is, mu basically decides where the PDF is centered. And by the way, the Gaussian PDF is supported on the entire real line. And so mu specifies where it's centered, and sigma specifies the breadth of the distribution. So higher values of sigma correspond to random variables, which are going to have a broader spread if you sample it many times. And one thing I wanted to mention is these terms which are highlighted in red are the normalizing factors which make sure that the PDFs integrate to 1. And it'll turn out in statistical mechanics, in the case of the Boltzmann distribution, these normalizing factors essentially contain all the information you need to know about the distribution. As a side note, these 2 distributions are also interesting in the sense that they are the least structured distributions if we impose some constraints on the observations of X. And you might see this later on in the talk. So we've been talking about PDFs and descriptions of a single random variable, but how do we describe the random occurrences of 2 random variables which might be related to each other? And the object we use to do this is the joint PDF of 2 random variables, X and Y in this case. And so here's an example of a joint PDF where the x-axis represents values of X and the y-axis is values of Y, and regions which are redder correspond to higher values. So right away you can see that how this joint PDF is encoding dependencies between the random variables. If X takes on a positive value, Y is more likely to be positive, and vice versa. So the dependencies in how these random variables fluctuate, or how the outcomes fluctuate together, is encoded in the structure of this joint PDF. And in the same way that the area under a PDF tells you what is the probability that a single random variable will fall within that interval, the volume under a certain box of the joint PDF tells you what is the probability that the pair X and Y will fall inside that box. And given the joint PDF, we can also extract the individual PDFs for X and Y, call their marginals, by integrating out the other variable. But usually you can't go back the other way, meaning if I just give you the marginals, you can't tell me the joint because it requires more information, and that information is about how are they related to each other. And the next thing we're going to look at is moments of random variables. So these are numbers which in a concise way summarize information about the PDF. And two common moments which you might have encountered elsewhere are the mean and the variance. So the mean gives you an idea. So the mean, which is defined by this integral, and where f of x is the PDF of x, is something which tells you which captures the notion like what's the central mass of a whole range of samples of x. So what's the average value of x? And the variance captures the notion of what is the average squared deviation of the random variable from its mean value. And the variance is a number which summarizes how much spread should you expect in the random variable when you sample it many times. And for a Gaussian random variables, the two parameters which specify their distribution end up being the mean and the variance. And two other moments which are interesting and important for two random variables are the correlation and the covariance. And the correlation is nothing but the mean value of the product of the two random variables. And the covariance turns out to be the mean of the deviations from the individual product of the deviations from the individual means. And what these two moments capture are the dependencies between x and y. So if two random variables are positively correlated, then if you sample x and y several times, sorry about that. If you sample x and y several times, then positive values of x co-occur with positive values of y more often than not. And if they are negatively correlated, the opposite is true. So here are examples of joint PDFs which will give rise to positive correlations, and a joint PDF which will give rise to a negative correlation. And we say that two random variables, x and y, are uncorrelated if the covariance of the random variables is 0. So here's an example of a joint PDF for which the random variables end up being uncorrelated. One thing I want to point out is although these moments give you a concise summary of the dependence, they leave out information. And for instance, if two random variables are uncorrelated, it doesn't mean that there is no dependence between them. And to look at that more closely, we need to get into the notion of what dependence means. So that brings me to statistical independence of two random variables, which is defined as follows. So two random variables x and y are independent if you can write their joint PDF as the product of their marginals. And this captures the notions that outcomes of x are unrelated to outcomes of y. And it's a pretty strong condition. And if x and y are independent, you can show, and it's an easy exercise, you can show that they will turn out to be uncorrelated, but the converse is not true. And here's an example where that's simply illustrated. So if here, if X and Y are independent, for instance, they have this PDF, then you're guaranteed that they're uncorrelated. But let's say they have this PDF where most of the PDF mass is concentrated in a very narrow ring, a circular ring, then they are uncorrelated, but it turns out that if you observe a certain value for X, then the values of Y which are likely are very tightly constrained. So they are strongly related in the sense. So uncorrelated doesn't imply independence. That's something to keep in mind. The last thing I want to touch upon in this primer is a very rich and complex topic, which has to do with the notion of entropy and information in random variables. And we're going to be barely scratch the surface of this topic. The Shannon entropy of a random variable captures the notion, it puts a number on the idea of how random is a random variable. And it's got to do with the uncertainties which are associated with the outcomes of a random variable X. And for technical reasons, it's easier to talk about it when you have discrete random variables. So let's say X is a discrete random variable, and it takes on, the outcomes can be Xi, and Pi is the probability which is associated with the particular outcome Xi. Then the entropy of X is defined as this following quantity, which is the sum over I of Pi log Pi. And what Chen showed was, if you assume some very general requirements for any notion of information, then this particular definition of the entropy or information in the random variable is the unique form up to constants. And the constants have to do with what base of the logarithm you choose. And if you choose logarithm to the base 2, then entropy is measured in bits. So let's take an example. So coming back to our fair coin, or not a fair coin, just any biased coin. Let's say P is the probability of getting a heads or a tails, it doesn't matter. The probability, the entropy of the random variable which represents the coin flip is then given by this formula, and it's plotted over here as a function of P. And you see that it goes from low values to a maximum value and then goes back to a low value again. So the entropy is maximized when P is half, meaning the coin is fair. So it's the most random in a sense, like you can't predict what the flip is going to turn up. However, when P is 0 or 1, the entropy is 0, meaning the coin flip is almost like a deterministic process. The other important quantity, which I want to just briefly mention, is the notion of mutual information. So the entropy captures how much randomness there is in a single random variable. But let's say you have two random variables which are fluctuating, and you want to have some number which tells you how much information do the fluctuations in some random variable X, how much information does that convey about fluctuations in Y? And that is captured by this quantity I called mutual information, and that's nothing but the entropy in X plus the entropy in Y minus the entropy of XY, where this entropy of XY is calculated using the joint PDF. And it'll turn out that when X and Y are independent, the mutual information is 0, which makes sense, should be intuitive for any definition. And then it also turns out that the entropy of the joint random variable XY, the pair XY, is nothing but the sum of their entropies. So that was a very quick, very brief touch on entropy and information and some concepts in probability. And I'm going to turn it over to Caroline. But if you have questions, please do on this part of the talk, do post them on the chat room, and I'll try to answer those.
All right.
All right, I guess, Kamesh, do you want to answer just one or two questions in the chat? So one is, Subhash asked, could you explain the meaning of covariance between quantities X and Y intuitively?
Yeah, so the difference between the correlation and covariance has to do with the following. Like if X and Y have means which are non-zero, and they happen to be independent, it will contribute some positive value or some non-zero value to the correlation. So the covariance is supposed to take away the contribution just from the mean values. So it is nothing but the average of the product of the deviations from the mean. And if two random variables have zero mean, the correlation and the covariance are the same. That's the basic idea.
Okay. Should I get started then?
And if there are other questions, so maybe Caroline should get started. And if there are other questions, I'll try to answer them over chat, or we'll hopefully have some more time at the end.
Yeah, sounds good.
Yeah. All right, so I will get started. You guys can see the screen, right? John, Kamesh at least? Okay. All right, so we are going to talk about maximum entropy models, right? So max, let's make that somewhat smaller. Right? Right? And let's talk about that first by taking an example, right? So let's say I tell you that there is a system and you know what the mean and the variance of that system is, right? So I know, oh shit, it's not working. One second. I'm sorry, one second. I'll talk with my, whatever. Okay, so let's say I have a system and I know the mean and the variance of that system. So my system, but I don't know the probability distribution, right? And so I'm trying to make some sort of guess as to, so I want to take that information that I have, the mean and the variance of the system, and I want to make a guess about like what this actual probability distribution might look like. I'm sorry, this hopefully will load and I can actually talk by writing, which is a lot easier, but we'll just keep going this way. Okay, I don't know where I was just writing went. We will start a new one. Sorry.
It's all good. Take your time.
How do I? Sorry, how do I, it's not, whatever, let's just go back to, sorry, we're gonna switch apps. Okay. Okay, we can write here. All right, sorry guys, don't know what's happening with technical issues, but it's fine. So, all right, so as I was saying, let's say we have a random distribution and we know mu, so we know the mean, and we know sigma squared, so we know the variance, right? So essentially what we're saying is we know about how wide our distribution is, we have one measure of how wide our distribution is, and we have one measure of where the center of our distribution is, right? So what that means is there's a lot of different probability distributions that could satisfy those conditions, right? There's one that is maybe the natural to draw, which is something like a Gaussian or a normal distribution, right? But I could also draw something that looks like this, right? And that will have the same mean and it can have the same standard deviation or variance, right? And similarly, I can draw something much more complicated that looks like whatever this, right? And those all will fit the constraints I'm saying, right? Which is that I know what my mean and my variance is. And so fundamentally, that's sort of what the problem of maximum entropy is, right? It's saying I have a couple of things that I know about my probability distribution, and how do I choose one, choose like a representative probability distribution given the things I know, right? And so looking at these, you might think, well, this seems like a silly choice because, I mean, why would I guess that there's a wiggle here given that I only know the mean? And this seems like a pretty strong choice, and maybe this is the natural thing to choose. But maximum entropy is sort of a way to make that intuition that this feels more natural, this top one feels more natural because it's less of a strong choice, and it feels like you're not saying as much, making that really quantitative. Cool? Okay. So in order to make that clear, let's take a second and let's talk about entropy. So Kamesh talked about this a little bit, right? So entropy, and we are going to work in the continuous case here. So entropy, which I will call H, is generally, right, the negative integral of P of X log P of X integrated over X, right? And entropy we can think of as a lot of things. If you remember from a statistical physics class, you might have first seen entropy when it's sort of posed to you as something like the log of the number of states, right? And that's sort of useful for intuition here, right? What we're really talking about is like entropy sort of tells you about like how much you know about your system, right? If there's only one possible state, then you know exactly what your system is doing. Whereas if you have many available states, then it's possible for you know much less about exactly where your system is, right? And the entropy is higher. Similar, so that is really what this is, right? So like if I think about something like, let's say I know that my state describes like a probability distribution in a box, right? So let's say I have, like, let's look at 3 different possible probability distributions, right? Let's say I know that let's make this specific. Let's say I have a particle and I know it lives between A and B. And I'm just looking at probability distributions of like, where could my particle be, right? So one of those is I say that the probability distribution looks like this, right? And what that means is that I know exactly where my particle is. There's very little entropy here because I know almost everything. There's no uncertainty and there's very little entropy, right? Similarly, I could say it's something like this, right? And now we're saying that there is a lot more uncertainty about where my particle is in this box, right? It could be more places. And finally, we can say something between A and B, which is it's just a uniform distribution here. It's completely flat. And then what we're saying is that the particle could be anywhere in this box and it's equally likely. And so we have as the most uncertainty we could possibly have about the position of the particle. So in general, really what I'm trying to get at here is entropy is really sort of just a measure of what you would intuitively think of as like uncertainty about the variable. That's really what it is. And when we say maximum entropy, what we are doing is we're saying that given the constraints that we have, so here, for example, mean and variance, what is the probability distribution that would give us the most uncertainty? So where we're not saying something very specific, right? Like if I took this mean and variance and I went here, I would be making by going from one to the next, would be from the mean and variance to this distribution with 2 peaks, we'll be making a really strong claim about, I think it's in one of these 2 peaks. But by doing something by saying like, let me keep the maximum amount of uncertainty, I'm trying to sort of make as little claim as I can about where the particle is. Okay. So let's go back to maximum entropy. So given that, I want to take, and assuming that is fine, it is hard to tell when you don't see the people you're teaching. let's go back for a second and talk. I want to talk a little more specifically about how we actually do maximum entropy calculations. So again, what we want to do, so we're saying we have some constraints, right? So we know, let's say, mu and sigma squared, right? So we know the mean and variance of our distribution. And so what we're saying is that we want to maximize the entropy, right? So we can write that down. H of p is negative integral of p of x log p of x dx, right? And we want to maximize that, but we want to maximize it subject to some specific constraints, right? So we want to, and when I say maximize, I mean subject to, like, what is the function p, right? We want to choose the function p of x that maximizes this and keeps these constraints of mu and sigma squared. So in order to do that, we use a mathematical tool that some of you might remember from, like, a classical mechanics class called Lagrange multipliers. Right? And these are basically just a trick we can use that allows us to do maximization of a function while keeping other specific constraints about how our function looks, like while fixing specific things about our functions, right? And so let's start by just writing out what the constraints are here are. So we have a couple of constraints when we do this maximization of this function, right? So first is just this normalization that Kamesh talked about, right? So if you just naively were going to maximize change some function, like, the math doesn't know that p is supposed to be a probability distribution, right? So it doesn't know that, like, we need it to be normalized. A probability distribution where the total probability is more than 1 is sort of meaningless. So we need this probability distribution to be normalized when we solve this. Additionally, we want to fix the mean. So we're saying the integral of x, p of x, dx equals mu. And this is whatever mean we are saying we know. And the integral of x minus mu squared, p of x dx equals sigma squared. Okay, and so these are the constraints we want. In order to do this, what we do is we can write down some objective function. Let's call it j, that we're going to maximize. And j is this thing we want to maximize. So h, right, is negative p of x log p of x dx plus lambda. And this is the Lagrange multiplier times integral p of x dx minus 1. So here, all I'm doing is I'm multiplying the Lagrange multiplier by something that we want to be 0 in the end, right? This is something that should be 0 if we have satisfied our constraint, right? And this is what I'm saying is it's a sort of a mathematical trick that works for these things. And then it turns out that in this case, I actually don't need to separately constrain both the mean and the variance. Variance is only really is defined around the mean. And so I can just add one more Lagrange multiplier and have a constraint here where I say the integral of x minus mu squared p of x dx minus sigma squared, right? So let's just take a second again and think back to all we've done here is we've said what we want to do is maximize h, and we've used one trick, which is Lagrange multipliers, right? Then what we do is the same way you've learned to maximize a function since forever, right? Which is you can take the derivative of j with respect to p, right? Right? And this is just -1 minus log p of x plus lambda 0 plus lambda 1 times x minus mu squared, right? And when you're trying to maximize something, you take the derivative and you set it to 0, right? And so we can set this to 0. right? This allows us to solve for log of p of x equals 1 minus lambda 0 minus lambda 1 times x minus mu squared, right? And then we can, then all we're doing is algebra, right? So p of x equals the exponent of 1 minus lambda 0 minus lambda 1 times x minus mu squared. Or we could write that as p of x equals some stuff, exponent of 1 minus lambda 0 times minus lambda 0 x minus mu squared, right? And so at this point, you should be able to see that we already have something that looks like a Gaussian, right? So if you remember, a Gaussian is just something that where p of x is 1 over some normalization, right, times the exponent of negative x minus mu squared over 2 things, right? So this already looks just like a Gaussian, and the only things are these Lagrange multipliers that are floating around, and those are just set by saying, by requiring that, like, we say that, oh, the integral of p of x has to be 1, and so we can do that and we can solve and we'll find what a Lagrange multiplier is. This is lambda 1. Sorry. Okay, so all we're doing here is, like, again, I just want to emphasize, like, I usually hate watching people do derivations, but I really kind of want to emphasize that this is actually not that complicated in theory, right? All we're doing is we're saying this is an entropy, we want to maximize it, and we want to maximize it with some constraints. In order to do that, we add the Lagrange multipliers, which are a mathematical trick that you commonly use when you're maximizing something with any particular constraint. We then just do traditional maximization, right? We just take a derivative, basically. And that gives us the function that we're looking for. And this is the Gaussian, right? So this is the first thing we were saying up here, is that if we have a mean and variance, the maximum entropy distribution, the thing with the most uncertainty that satisfies those constraints, is a Gaussian. Okay, I am going to wrap up in a second and skip talking about course screening. But the last thing I wanted to do was just make a few more points here. Like, again, so thinking about maximum entropy, again, it's just a question of, like, given a couple of constraints, what is the distribution with the most uncertainty, right? And so we can think of some other things, like, as I was saying before, if maybe the constraint you know is only that, like, x is between A and B, and I sort of mentioned this before, but if this is the only thing I know, right, so B is here and A is here, right? If X is between A and B, then that means then the maximum entropy distribution is the one with the most entropy there, and it's a uniform distribution on that space. And similarly, if I know that, like, let's say X is greater than 0, and I know that the mean, right? So it's in this space, and I know what the mean is, then that gives me a specific exponential distribution, right? So e to the minus x, right? And importantly, this is actually very similar to the question of, like, a Boltzmann distribution is actually a maximum entropy distribution once you know the energy and things like that. So again, like, it's too bad we don't have time for talking about course screening, but I just wanted to go through here, and, like, maximum entropy is just, you have a couple of constraints, it's the distribution with the most uncertainty. And then I think we should hand it over to Xiaowen while we still have extra time. Good?
Yeah. So maybe, Caroline, if you want to answer the questions in the chat, and then I will start sharing my screen. Caroline, can you stop sharing your screen?
Yes. Let's go back to wherever Zoom went.
Great, thank you.
Okay, so let me start with just the last one. So the maximum probability of any event is 1. What would be the example of a function which is not normalized? So probability distributions are, like, by definition normalized. But a function that is not normalized, for example, would be something like p equals 2 for all values of x or something, right? There's no, in general, a function doesn't have to be normalized, but probability distributions are, like, by definition. My point was that, like, in practice for this, like, if you just do maximization without requiring normalizations, there's no reason you should get a function that looks anything like a probability distribution. The question, how do we get rid of the Lagrange multipliers in the end of the derivation? That just comes out. So when I get to, so I wrote for you guys, like, sorry, let me go open my notes back up and remember exactly what I wrote for you. So I wrote for you guys this thing that, like, p of x equals exponent of, like, 1 minus lambda 0 times exponent of, like, negative lambda 1 times x minus mu squared. And what you can do is you say, okay, now we have two unknowns in that equation, right? Lambda 0 and lambda 1. And we have two equations for that, right? One of those equations is that the integral of p of x is 1, right? And that will that will tell you what one of those lambdas is. And the other equation that you have is that the variance has to be something sigma squared. And so that is enough. Like, you can, it's just algebra of setting those equations. Is there one, Xiaowen, should we go on?
Yeah, actually, maybe I can start talking and then
I can answer these in the chat too, yeah.
That's great, okay. All right, so now we know basically what is probability distribution, and then we also know what does maximum entropy model mean. We can look a bit more into detail of those papers and then to better connect physics and biology. So the main question we want to ask is really to characterize collective behavior in living systems using statistical mechanics. Right, and then first maybe just some schematics or real films of what collective behavior is in biology. This is some figure that you've seen from Professor Shavett's lecture a month ago as some bacteria colony forming interesting patterns. And the paper, one of the paper we'll talk about today is their bird flock. Pretty amazing how, you know, just bird forms flocks, and then which is not what you expect if you have a single bird. And there's also intra-organism interaction. So in our brain, our cognitive activities are generated mainly by the interaction among all those neurons, the basic unit of the brain. And another example is how genes regulate each other and again, forming a network. So the two papers today, one is about bird flock and the other is about neural network. So actually more in the upcoming weeks, the summer school will mainly focus on neural network. So maybe today I'll just focus on the bird flocks. Okay. I guess it's just to put what we're talking about in the context of what you have seen so far in the summer school. Usually when you're looking at, you know, trying to understand collective behavior in biology, you're trying to connect the local interactions to some global behavior. Right, like whether you see some fruiting body of the bacterial colony or you see a flock moving this way or the other. And most of the approach you've seen in previous lecture is this bottom-up approach. So you have some model theory about the local interaction, and then you predict something about what you will see globally, for example, the correlation. And the goal is really for your theory to successfully predict these collective features of the data. And if it doesn't work, then maybe you go back and then modify your model or theory. And maybe you have some parameter in your model or theory that you can tune such that it matches the data. But now actually with more and more modern technology, people can simultaneously measure many degrees of freedom in real biological systems. And then this approach is actually harder and harder because, or you need to go through many iterations such that maybe your model captures everything that's complicated about the biology. So an alternative approach is a rather top-down approach, and that is the maximum entropy model that we have introduced so far. And it's to directly infer local interaction rules from the data we collect. We'll talk about it in more detail using the bird flock example. And we can also maybe think a bit about what's the benefit of having a theory or model after all. Maybe you say, okay, we can just look at the data. So the benefit of a theory or model is really, if you have parameter, you can kind of see where the parameter of real biology sits. In terms of model, you can maybe tune the parameters and engineer some of the cells to do something that you wouldn't expect it to do in its natural environment. But for example, if you're interested in something that you know you have a theory that predict about the data, another approach is really just to use the data. So for example, that's the paper of Mashulam et al. Talk about, and then they're doing a coarse graining of neural activities. I won't go into details. I think Professor Bialek will talk about it more in his lecture, but the concept is really there is some theory prediction about self-similarity, and you can really just by looking at the data and have a self-consistent picture. Okay, so now let's go more into the bird flock. So some of you asked more about the biology of the bird flocks. Well, first of all, why do we want the bird to be flocking? The functional advantage includes it forms protection against predators, sometimes not specifically the starling birds, but it has some aerodynamic advantage for geese, for example, provide warmth for penguin groups. And also you can see in many other animal groups like a fish group or insects. Sometimes for insects like bees or ants, you will have more complex hierarchy structure. But here for the starling birds, particularly, it's not believed that there is any leader or followers. So it is more of this statistical mechanics picture where you can basically consider all the individual birds to be roughly similar to each other. So some bottom-up approach about bird flocks actually started with a VCHAT model in the 90s. And there they use something called a metric distance control interaction. So basically, if a bird is flying with a direction of S, they're saying, oh, well, the interaction is really, it's just going to align with all the other birds within a radius of R. And here, for example, this bird here is really outside of the circle, so the red bird is not reactive to the direction of this bird. So the prediction of this model, while it's successfully generate flocks, but there is a dependence on this R, this radius of interaction. So if you have a small interaction radius, you have small flocks. But if you have a large interaction radius, you have large flocks. Okay. So that's a very good model about active matter in general, but it's not really a good model for real flocks. I mean, if you're just looking at this picture, you already notice there are flocks with size just 10 birds and also with more than 1,000 birds, and the radius are very different. So that's not what the previous model predict. Basically, if you're saying all the birds just have a fixed radius, then you only expect to have one size of bird flock. So what can real data actually tell us? So the groups of Andrea Cavagna and Erin Giardina in Rome developed modern technology that can track the position and velocity of birds in this even 1,000 flocks simultaneously. That's very cool technique if you're interested in more. And from this, what you see is, well, a bunch of arrows indicating the velocity of the birds, and they're mostly flying in the same direction. So we can try to use maximum entropy model on this. Basically, from this picture, what you can get is something like how a correlation function decays as a function of the distance. Just as here, let's just ignore the red dots for now. So the blue dot just tells you how does the correlation length scale as the distance in a specific flock, but within here is how this correlation length increase as just the size of the flocks. So if you have this function, the decay of correlation, and what is done in this paper is to really form an inverse problem, and from the correlation, you're trying to get interaction. And the correlation, again, is some constraint of this maximum entropy model that we're trying to fix. So as what Caroline showed, the corresponding maximum entropy model is the probability distribution that matches this constraint, but otherwise having the maximum entropy or the least assumption otherwise is of this exponential class, right? And in particular, what they were able to show in this paper is actually it's a topological interaction that makes sense, which is really the birds only react to the next NC neighbor. So here is just a picture of NC equals 4. Well, what this is telling me is basically this distance can be 1 meter or 10 meter, it doesn't matter. I'm just, as a bird, I'm just reacting to my neighbors. So in this sense, my bird flock can be small or large, also doesn't really matter. And for larger flocks, I can get a larger correlation length. So what we did in this maximum entropy model, or people in the paper did, is they just inferred the parameters J, the interaction strength, and NC, the number of neighbors that each bird is kind of influenced by, directly from the data. And they were able to show that the neighboring interaction is enough to reproduce the data. I mean, here, the red dots is just showing that this maximum entropy model worked, in the sense that we can successfully reproduce the correlation versus distance using the model. So something to note is here is an effective Hamiltonian if we use the language of Boltzmann distribution, but it's not really related to the dynamics of the system. It's really just because mathematically, this maximum entropy distribution is equivalent to a Boltzmann distribution. So we call it the Hamiltonian. Of course, maybe you can further investigate, okay, what is, for example, the Langevin dynamics you will have using this effective Hamiltonian, and compare it to the actual dynamics of the bird and see, okay, if your system is out of equilibrium or not. But it's not necessarily a priori that this effective Hamiltonian tell us anything about the dynamics. Okay, so let's just go through a bit about what new things can this maximum entropy model tell us. So specific to this paper, what we learn is, well, our model only has pairwise interaction, but it's enough to capture higher order correlation of the data. And then here it just was shown in the paper how fourth order correlation, just a correlation among 4 birds, can be captured using data generated using this X-ant distribution. So as contrary to maybe some other study of bird flocks where they need to consider in like higher order interaction among birds, at least here, pairwise interaction is enough. And another thing is you can just have short range interaction. You're just interacting with your neighboring birds, and it's enough to produce a coherent bird. And to put it in the picture of related papers, also done mostly through papers from basically from the Rome group. okay, first is what are the functional advantage of using topological interaction threshold. It's mainly if you have a predator that comes in, the topological interaction will makes your flock more coherent. Rather, if you have a matrix interaction, the birds will get kind of dispersed. Subsequent papers following this 2012 paper also include some a maximum entropy model about the speed of the birds, and also some dynamical model by coupling nearby time points. So this max entropy model is really, it's a method. So it's not just applicable to this specific system, but it's also in many other contexts, like swarm ranges or school of fish. Maybe you will find different interaction from each system, and that's what's cool about this method. So you kind of can tease out this important information just from looking at the data. It's also used to study effective interaction among the neurons. And in many cases, because the parameters we infer here are the J's, the interaction. And it's just suggesting that real biological system sits near the critical point. And that's really cool as well. But we need to also notice that there are problems of using maximum entropy model. And one of them is really just the number of parameters we have. So here in this system, you know, we have J, we're assuming all birds interacting with the same strength. But it's not true in models of neurons. And really the number of your parameter goes exponential as your system size increase. So it's very intense computationally. So if we're only interested in, for example, probing whether real biological system sits near the critical point, maybe there are other ways of doing it by not even looking at the model, but just looking at signatures of criticality directly using the data. So that's something that Mushroom et al. Did. So they were just using some coarse graining procedure and trying to see if there's self-similarity in this group of neurons. Okay, so yeah, I will stop now and take questions. Let's see. So one of the questions I can answer, Pranit's question, are the number of neighbors for each bird a constant? So it's not, well, it depends on how much you consider the neighbors, right? I mean, the birds is in a flock and has many neighbors around it, but this model here is actually just telling us the number of neighbors that is impactful on this bird is just a constant. Well, you can imagine if you're at the edge, maybe you have less neighbors than birds in the center. So that is, that's a valid point. And in this specific paper, they fixed the edge birds. And I think, I mean, it's still ongoing research. Question. Okay, and then Krishna asked, in bird flock study have shown that roosting happens in waves, possibly to facilitate information transfer on food sources and dangers. How much could this information affect the mean direction of movement of the flock? Is it largely driven by the stochastic choice made by the border individual instead, or perhaps a combination of both? I think there are studies for each, right? Like there's some study on how external source will impact the motion, as well as how some random fluctuation impact the movement of the flock. And those, I guess you can't really distinguish. But There are studies, for example, in a 2014 paper, I can leave it in the chat as well. Mostly the turning direction is initiated by birds on the edge. And it's also really cool to study how basically the wave propagates through the bird. And again, this dispersion relation, actually they can show it's different from predicted by a WeChat model. So I will leave more information later. So how does, Jessica asks, how does the bird determine which neighbors to pick if distance from its neighbor doesn't seem to be a parameter that affects it? It's just the closest birds. So for example, if I'm in a crowd, really, I have a bunch of birds around me and a bunch of birds around the birds around me. And really it's just the ones that's closest to me. Yeah, I think another thing, I think I know like the time is almost up as well. I'm not sure. Maybe the best way is for me to also answer this question later in the chat. I'm not sure. Right, anyway, I should leave my slides up because there are also information about our emails. So you can actually just email any one of us with your questions. Yeah. Yeah, we'll stay online for a bit just to answer the remaining questions in the chat. But otherwise, Caroline and Kamesh, do you have more things you want to share?
I think apart from the questions, I'm all good. But yeah, thank you, Xiaowen and Caroline, for.
Oh, that's okay.
Okay.
All right.
All right, thank you.
Well, so should we hang around and we'll finish typing up answers? So
Yeah, I think we can do that.
All right. So yeah, we're here to answer questions.
Yeah. Okay, so I'm done with that. Question, Prajwal, sorry if I pronounced your name wrongly, is asking if essentially maximum entropy model says the model is the simplest model that's consistent with the data. That is true, but that might not give any additional insight into the system. So that's not necessarily true. So for example, in the bird, it's basically saying, yeah, exactly. It's giving us the simplest model. But for example, in other cases, for example, models of neural network, what people found is, for example, well, first you build a probability distribution using just pairwise interaction, and then they can they have some further investigation, and then seeing mainly you have this resulting distribution, and the system can actually use the local peaks of this probability distribution to store information, to store memory. So that's pretty cool. And that's not something you can find by just directly looking at the data. I mean, I guess you can, but using maximum entropy model, it's a way to construct a probability distribution that and doesn't require like an infinite long data stream for you to answer those questions. Okay, and then you ask, start from the model to data approach, you can verify if the model will hold across different biological systems, but the maximum model gives a data consistent probability distribution for every biological system taken, because it's just, it's similar to parameter fitting. That's correct as well, but again, I mean, for different systems, depends on how the interactions are different. Maybe in some systems, it's better to choose like pairwise correlation as something to constrain. Some other systems, it's best to choose, for example, the number of k out of n individuals being in the same state together. So I think it's really, it's a method. It's a way of, the same thing is to construct distribution from data. And you can compare it because it's all exponential class distributions. But I think the details are not necessarily, you know, like you can't really compare like the interaction strength you get from one model's, like the birds, to the strengths you get from neurons, something like that.
Okay, sorry, I just wanted to go on to the next questions.
Yeah.
So a couple people ask about the questions of like, are the birds only, shouldn't birds really only be affected by the birds in front of them, or who they're looking at, or who they can see? And first of all, yes, you could write a model, like a Weak-Schick model, for example, where the birds are only affected by those in front of them. Definitely, that is totally possible. In that case, like, it's in some sense, it's just a matter of taste. You can always add details to a model that you're building, and those details might describe something, but at some point you wonder if, like, in order to do that, you have to make a decision about which birds can this bird see and how strongly does it weight the birds in front of it versus the birds behind it or something. And so sometimes you might say, and I think a lot of people would say, that maybe it's better to just say, let's not make any really strong claims about who this bird is looking at, and let's just go with the simplest model and hope that that gets us something more general. Does that make sense? Cool. And so there's a couple of people asked about that, but hopefully that answers that. I can answer this question about entropy also. There's a question here about if we think entropy is a function of the nature of the system alone, or if it's a function of both the nature of the system as well as our knowledge of the system. So entropy is a function of a probability distribution, right? It describes, it's a quantity that comes out of a probability distribution. It is about the system. It's a quantity that is in the system. We talk about it as something like how much uncertainty we have about this, what the state is or something. But really what we mean is, like, if I know the probability distribution, how much, like, really what we're saying there is, like, if I know the probability distribution, how much uncertainty do I have about the specific instantiation of what the system is doing? So it is like, it is completely independent of what I know or what I'm thinking or anything. Entropy is just like a function of a probability distribution. And at some level, you could think of it as like the same sort of thing as a mean or a variance or something like that. It's a number that describes a probability distribution. Is there stuff you guys want to answer?
Yeah, I can answer the question to Carlos, of Carlos. So Carlos asks, what is the relation basically between the bird flock we were seeing versus Ising model, and specifically the transition from magnetic to non-magnetic? So it's a good point. And in particular, if the interaction of the birds are not very strong, then you would imagine in each bird just flies into its own direction. And but when your interaction is strong enough, then the birds are aligned, and then you can kind of form a flock and then flies together. So in the case of it's condensed or not, I think in particular, this paper, the bird flock paper, didn't really talk about the spacing between each bird. So that would be another transition, but really it tells about the alignment. So in the transition sense, it is similar, but not the packed and unpacked case. Yeah.
Maybe I can answer this question about topological relations versus metric relations. So the idea is topological relations encode some notion of connectivity. So think about if you were to make a graph with birds as the vertices and the neighbors as the edges, and you don't draw an edge outside some radius. But within that radius, like if the birds move around, the edge still remains. Like there's no specific value associated to the edge other than the fact that there exists an edge or there doesn't. Now that would be a topological relation, but a metric relation has to do with the fact that if you pull things apart, the Euclidean or whatever your favorite metric is, that value is going to change. And so those distances will change, whereas the topological relation still remains the same. So sort of at an even more abstract level, the topological relation captures a notion of inclusion within sets and what's outside the set. So in this case, the sets will be neighbors. Whereas the metric relation actually puts a number on this, right? Like, which is how far you're away from me. And when you say that topological relations matter and metric relations don't matter, what it really means is some number you're calculating really depends on who are your neighbors and not necessarily like how far they are from you. That's.
Okay, and then I can answer Mustafa's question. So how do you differ correlation from direct relationship in this particular subject? So in terms of birds, maybe you can think, okay, two birds, if they're interacting through a common neighbor, then okay, A, B, and C. A and B are close to each other, so B influence A, and then also B influence C, and it's like you know, A also to B and C also to B. So from the data, it will appear that A and C are correlated. So that's some correlation that you directly see from the data. But the direct interaction would be just between the neighbors. So that's also how, I guess one advantage of what this maximum entropy model can tease out is using this correlation that you infer an interaction matrix J and some rules, and you can then tell the difference that, okay, if you realize the number of neighbors that's effective is really just one, then you can tell that A and C is only correlated, but there's no direct relationship or interaction.
Okay, there's a question to me which is asking basically, do you do knowledge inference from deep learning networks? There's a few variants of this type of question which are addressed in the group at the CPBF. So I personally work with collaborators who sort of think more about the theory aspect of things, which is like when deep networks or recurrent networks work well, like what mechanisms in them make them work well. But if you're interested in working with data, I recommend checking out work in Professor Shiewitz's group. There's some really exciting work. Just Google for sleep, check out Talmo Pereira's work. And what they do is they take videos of flies or animals moving around, and they use deep networks and other techniques to figure out the poses, meaning figuring out where the limbs are, what positions they are in. And so in that sense, like there's deep learning used in inferring pose and other information from complex natural behavior.
I can, so, well, okay, I'm not sure exactly where we mean by, so the question is, here the indexes I and j refer to certain positions in the flock as opposed to individual birds. In this, are we assuming a particular structure to the flock where there are a number of sites which the birds are occupying? So I'm not sure if there's a specific place I should be thinking of. You're looking at, in general, when people are talking about beak-shaped metals and things, they, I and j do refer to a bird. Yeah. Do you have more, John?
Yeah, I can add a bit to this answer. So in particular, in this paper, they're really looking at just a snapshot of the bird flock. So the bird isn't moving. So you're really considering, okay, I and j are referring to an individual bird, but it's also, you know, fixed in the location. And then there are subsequent work that look at the dynamic models, and then they can actually show that if you're looking at birds, you know, for a short time, or how fast it adjusts itself such that it aligns with the neighbor is faster than how the neighboring birds change position. So in that sense, locally or at each time, you can really consider the bird to be, you know, like a fixed structure. Yeah. Okay.
Maybe it's a good time to wrap up.
Yeah, I think we're done.
Yeah.
Cool.
Okay, thank you all
Bye,
for
everyone.
joining us.
Yeah. And you can, again, email us if you have any more questions. And yeah, hope you enjoy the later lecture by Professor Bialik. All right, thank you.